Okay, cool. So um, we're going to start talking. We're going to jump right in, start talking about vectors in uh, 2 dimensions and 3 dimensions. We're going to jump right into that. So at this point, most of you have taken probably, hopefully, you've taken single variable calculus, and then maybe you've taken some other stuff. Maybe you've taken some kind of like differential equations or linear algebra class. But at this point, you've at least taken the basic calculus, what we call single variable calculus, and now in this class that we call multivariable calculus. So part of this is, when you're studying single variable calculus, all of the objects you're studying are functions which take in one number and they spit out one number. And what we're going to learn about in this class are functions that can take in multiple numbers and spit out multiple numbers. And so that's kind of what we need to learn about. But in order to do that, we first want to just study the basic geometry of the geometry and the algebra of multidimensional space. So 2-dimensional space, 3-dimensional space, and even later on we'll get beyond 3-dimensional space, which we'll talk about more later this week. So yeah, so like just think, before you were able to take calculus, you had to learn the algebra of single variables, right? You had to learn like what a function was. You had to learn how to solve equations and stuff like that. And so now we have to do that, but with higher dimensional objects. Okay, so let's first talk about the difference between 2 dimensions and 3 dimensions, which maybe is a little bit of a review for some of you if you kind of have an idea of what that looks like already, of the differences. But let's see, we've seen like a coordinate plane before. We see a point on the coordinate plane. The way we identify this point is you say, okay, well, this point has a certain height, right? And that height there is called the y coordinate. See some people in the chat. Let me see. Oh, someone's already shared a Discord link. That's cool. So we have a certain y coordinate, and then we have a certain x coordinate. And this point is given by just these 2 numbers. And the fact that there's 2 numbers here is why we call this the 2-dimensional space. So this is 2-dimensional space, right? In 3-dimensional space, we're all familiar with, because it's like the universe we live in is 3-dimensional space, right? But the reason it's 3-dimensional space is because if we try to give it coordinates like this, we need 3 numbers in order to keep track of all of the possible points. So this is 2-dimensional space because you only need 2 numbers to keep track of it. And usually we give these 2 numbers, but you can also do things like polar coordinates. But even if you're using polar coordinates, it's still 2 numbers, right? A radius and an angle. But in 3 dimensions, we can also do some like a coordinate system for 3 dimensions. But instead of these 2 axes, you'll get a 3rd axis out here. Okay. Now the way we label these axes. So for example, if I have a point, let's say it's up here, which maybe it's not clear exactly where this is, but let's say it has a certain height and then a certain distance here and a certain distance here. Okay. So then just as a convention, right, we always put this first coordinate in 2 dimensions. We always put this first coordinate is always the horizontal distance, and the y coordinate is always the vertical distance. That's just kind of how we do it. So that's what we always have. This is your x-axis is always down here, and your y-axis goes up and down like this. With 3 dimensions, the convention is a little different. So we have x is coming out of your screen like this, y is down here, and z is this thing popping up. So the way that works is, the way you should picture it is you take this coordinate plane and you kind of put it down on the table with the x-axis pointed at you or pointed towards you. That's how I picture it. You have your xy plane, and you kind of do this weird thing where so this is your xy plane. You kind of lay it down like this, and then you throw your z-axis as going straight up like that. Okay, so there's this added dimension of this z-axis with something like this. Okay, so this point is x, y, z. Okay, cool. Again, maybe a little bit of a review there. Maybe you've already seen something like that before, but these are the sort of objects we're going to be dealing with a lot this quarter. So you should have a good idea of what these things are, and we're going to get hopefully as the quarter goes on more and more comfortable with what this looks like with just working in higher dimensions. Okay, cool. Okay, so the next object of study, the big object of study that we're really going to deal with in this class is our vectors. So here we have this word vector, and this is sort of an object that it has direction and magnitude. Maybe you've learned about this. So some places you may have learned about this before is if you've taken maybe certain math classes before, but probably you've seen it if you've taken some kind of physics class. I think that's, other than a math class, that's probably the most common place you'll see something like this. It would be a math class, a physics class. And so if you're a physically minded person, if you like physics, then you can picture a vector as kind of, maybe a velocity vector or a force vector or something like that. So you've had some intuition of what this is. So when we start talking about it geometrically, geometrically a vector is, and so if you look it up in the textbook and you try to find a definition for what a vector is, they say something like it's a directed, a vector is a directed line segment. So let's break this down, what they mean by this, right? So I ripped this from the textbook. And what do we mean by a directed line segment? Well, it's a line segment because, it has a start and an end, and it's like a straight line in between, right? And so it's a line segment. And then the directedness means it has a certain direction, right? It goes in this direction. It doesn't go in the opposite direction, okay? So that's kind of what we mean when we say it's a directed line segment. And, you could picture it living in either 2 or 3D space, right? So you can have line segments in 2D space, you can have them in 3D space. And again, later we're going to learn about what it means to even have them in higher dimensional space. But then what about algebraically? Well, maybe you remember this again from some other, maybe like a physics class. Basically what you can do is you can say, okay, well, I can picture this vector just kind of living abstractly in 2-dimensional space, or I can put coordinates on my 2-dimensional space, something like this, right? Or maybe you're picturing it in 3-dimensional space, so there's a third axis coming out, right? So you have your x-axis and your y-axis. Then what can you do with a vector if it's living in 2-dimensional or 3-dimensional space? Well, you could break it up into its base components, right? You can break it up into the x component, which would look something like this. We should make sure that's straight. So you have something like that, okay? And then you can break it up into its y component, which would look something like that, right? So this white vector here, we can break it up into this x component and this y component, right? Just like a point in 3D or in Cartesian coordinates, you can break it up into its x and y coordinates or x, y, z coordinates. You can do the same with a vector, except you're breaking it up into components that are also vectors, right? Basically, if you're thinking of this as an instruction, right, or a direction you need to move, you can move in this direction by moving this direction first and then this direction, right? So you can break it up like that. But how does that relate to the algebra side of things? So when we talk about vectors algebraically, a vector is an ordered pair. Well, if it's 2D, then you only need two numbers. A pair is two numbers. Or ordered triple. So an ordered triple is just like an ordered pair is two numbers that are in some order. An ordered triple is three numbers in order, right? So you have ordered pair or ordered triple. Okay. And so for example, this vector, this white vector here, and I'm going to give some hints on. I'll talk a little bit more about the notation here. Is the vector x comma y, and notice I'm putting these angle brackets here, and I'll talk a little bit more about that in just a second. Okay. But basically, there's these two things happening. There's the geometry, which is the pictures that we draw about vectors. And then there's the algebra, which is the notation we use using like numbers and different symbols like that. Okay. And I think having an understanding of both of these is important, right? You need to have the geometry because you need to be able to picture what's going on, right? In order to get anywhere, you're going to have a picture of what's going on. But you need to also understand the algebra because that's the best way to communicate it. So like on an exam, or if you're like, eventually, if you're explaining this to someone else, if you're, in some other class in the future for your major and you need to talk about something with vectors, you need to understand the notation too, so that you can communicate it with your peers or with whoever you're talking to. And algebra tends to be like a concise way to do that. And it's also a way of like checking your work and making sure that your intuition is correct. That's kind of how I understand these two. It's like, on one hand, you have the intuitive picture you have in your head. On the other hand, you have the notation that you use to justify all of that intuition. Okay, cool. So let's talk a little bit about this notation. Maybe you're noticing I used angle brackets here. With points up here, I used this little parentheses, and now I'm switching to angle brackets. Okay, a couple things, just because it's the first lecture, so I want to kind of clear things up. My handwriting gets kind of sloppy, especially the stuff that I'm writing as we go. Some of the stuff I had written already, and that stuff tends to be a little nicer because I'm writing it out slowly. As we're working, I tend to get sloppier as I get lower down on the screen. So if there's ever anything that you can't read, please feel free to reach out, ask in the chat, or raise your hand or whatever, and I'll respond. Okay. Cool. And if you have questions at all during class, like this time is for you guys. I'm working for you guys. So if you have questions, feel free to chime in and ask them. Okay. Cool. Also, if I'm moving too fast through the slides, you can ask me, but I'm gonna move on to the next one. Okay. Here we go. So yeah, so this is where I'm gonna talk about vectors. So vectors. This is how first of all, how do I like to write vectors? You may have noticed in the slide before, I like to write vectors as either, XYZ or XY or XYZ. And here, the letters aren't important. Those are just placeholders for some numbers, right? These are just going to be some numbers eventually. What I'm pointing out here is I use these pointy, what they call angle brackets. If a lot of you are at computers right now, you might see like the less than or greater than sign. That's a kind of how we use it's those symbols there if you're looking down at your keyboard. But in the book, and I should say also and hence the online homework, they like to use this notation here with parentheses. So it's different symbols on the keyboard, right? Or XYZ. Okay. So I like to use the pointy brackets, and the book likes to just use the normal parentheses. Now, why is this? Why do I like to use the pointy brackets? Is because I feel like the parentheses should be reserved for like when we're talking about points, and then the angle brackets should be reserved for when we're talking about vectors. But in the book, also they kind of conflate those two, and I'll talk a little bit about what I mean when I talk about the difference between a point and a vector. But a lot of the times they kind of just mash those two concepts together and say a vector and a point are basically just the same thing. And I'll talk a little bit more about why we can do that in just a second. or maybe I might do some examples first, but to start, you kind of, I just want to highlight this difference. Now, sometimes I'm hesitant to like use different notation in the book or something like that. One of the reasons I want to is because you might be in a class in the future and they might change notation. Okay. And so it's important that you see different notations early on and you get used to the skill in your of kind of going from one notation to a different notation and not being too thrown off by it. Okay. So if you're in lecture and you see me writing a bunch of angle brackets and you go and you do the online homework and there's not an angle bracket in sight, don't be too thrown off by that, right? It's just a difference in notation. And if I do diverge from the book, I will try to highlight it like I do here. Okay. So, and then another notational thing is, so this is like if you know the coordinates, right? If you're writing it as an ordered pair, but sometimes we just want to say, let this thing be a vector, and you don't always necessarily write the whole coordinate x, y, z or x, y, right? You're just going to write one symbol. We just want to write one symbol. In that case, if I was writing it down, I would write, whatever the name of the vector is. So maybe if it's v or w or something, v, w, u, those tend to be the letters that we use for vectors. I would write it like this, which is the little v, and then above the v, there's this little arrow thing that just tells you that, hey, this v is not just a regular old variable, it's actually a vector. But if you're typing or if you're reading something that was typed, they'll probably just use bold. Okay. Yeah, so someone's asking if there's other notations. Yeah, so some other notations that I'd never use. I've seen like v with just the line over it, or v with the arrow thing down here. I have a hard time drawing that one. But v with just the arrow thing down here. Also, another note, sometimes when people are on Zoom and I'm sharing screen, they sometimes get this bottom part cut off. If you can't see the bottom, please let me know. What else have I seen? I think physicists like another notation, but I think the other notations I know of are for other specific types of vectors, not just any old vector. But I think this is the second most common after this. Good question. Yeah. Yeah, and that'll also come up. There's also going to be like other notations that I can't necessarily get to or that I just don't know about because, because I'm just because I've never been exposed to it, right? So like I'm just for context, I'm not a physicist, I'm not an engineer or anything like that. I'm a mathematician, so that's kind of what I've been exposed to, and I've seen some other things, but I haven't been deep into anything else. So you might not always see me mention every single notation. Okay, but I think in the context of this class, I like to use this, or if anyone is writing, they'll probably use this. And then if something is typed like the homework or the textbook, they're just going to make the letter bold. Okay. Yeah, I think any notation, as long as it's clear that it's a vector, will be fine. And on like quizzes and stuff, if you're handwriting something and turning it in, just it's not terribly important what exactly notation you're using. Okay, cool. Good questions. Yeah, so like I said, this was kind of the basics of what vectors are. Now we want to talk about like how we actually use vectors in like algebraically. Just like before we learned calculus, we had to learn how to do algebra, right? And we had to learn about functions, but before that we had to learn how to like solve equations, and before that we had to learn like arithmetic. And that's kind of what this is. I called it the algebra of vectors. Some people might even be tempted to call this like the arithmetic of vectors. Okay, so maybe I'll even write that in. Maybe that's like a better name here. Maybe I'll say like arithmetic. Okay, so that's just an alternative name. Okay, so basically we can add and subtract vectors. So for example, if I take a vector a, b, c, oops, I'm already doing that, and I add it to a vector x, y, z. Okay, this would also work with 2. I just want to show it with 3 because it's kind of like the the big case. But you can imagine if I just had two things here and two things here, they do have to be of the same dimension. I will say that you have to have 3 and 3 or 2 and 2, right? Okay. Then the way we add these together, right, is we just add together all of the coordinates. So this is a plus x, b plus y, and c plus z. So the way I picture this is we're just like putting these two or the notation, I'm putting these two ordered triples on top of each other, and then I'm adding each of these coordinates together. 1, 2, 3, boom. Okay, and subtraction works the same way. So if you have a, b, c minus x, y, z. Okay, I did it up here too. Okay, then this is just a minus x, b minus y, and c minus z. Okay. Okay. Cool. So this is simple enough to understand. Like, it's simple to write down these equations, but it's also good to have some kind of intuition of what's actually happening here. And the way we intuitively work with vectors is we draw pictures of what's going on in the geometrically, right? And so in this case, I'm going to have two vectors to start with. So I'm going to start with a vector. Let's call it. Well, let's first set up a base point. So we have all of these vectors always have like a base point here, which I'm highlighting. I've also been told that the dot background that I use can get kind of confusing. So if you ever see something that's confusing to read, like if the dots look like decimals or something, please feel free to like ask for clarification on what I wrote, and I'll let you know. So for vectors, let's say we have this vector here, which we're going to call like u, and another vector maybe going out this way, and this is called v. Okay. You might be wondering, okay, how do we add these together? If you've ever taken again like a physics class or something, you've maybe learned how to add vectors together, right? So if I want to add these two vectors together, what's like the secret to do that geometrically in terms of the pictures? How do I add vectors together? Anyone know? Anyone remember from maybe some other class? Find x and y values. So I could like break this down and find the x values and the y values. But yeah, so this is kind of what I was looking for. Some of these other people, like the geometrically, it's you're doing like a head to tail thing, or you're turning these two into like the sides of a triangle, and you're figuring out that third side. So what you do basically is you take this vector, okay, this u vector, you make a copy of it, which is easy to do on a computer. Maybe it's harder to do if you're writing this down pen and paper. And you put the tail of u on the head of v. So you put the base of u on the tip of v, and then you just see where you end up. So basically, you go here and then here, and then that's kind of telling you where you end up. So you do this in another color. And this here in this like pinkish purple color is u plus v. Okay. Okay. Cool. So that's u plus v. Anyone remember how we find u minus v in terms of the picture? That in red here. In terms of the picture, how do I do u minus v? Someone's saying like a 180 head to head. Yeah, so head to head I think is kind of a good description. What we do is we connect one head to the other, okay? So in this case, we go from the head of V to the head of U. Oh, that was not very straight. Okay. And that's our difference here. So that's U. This in red is U minus V. Okay. Now, I think U plus V people tend to get because U plus V and V plus U are the same. But yeah, some people are, already in the chat asking, how do I know which way the vector goes? Like, how do I know, like, once I make this cut here, how do I know I don't go the opposite direction? How do I know I don't go from here to here? U minus V always goes from V to U. So U, let me write that down. U minus V goes from V to U, right? So you can, if you're the memorizing type of person, you can try to memorize this. But I like to have a picture of like why I get this or why this happens. Kind of what I like to think, instead of thinking of U minus V as a subtraction, just like in single variable stuff, you can turn any subtraction problem into an addition by the negative, right? So what you can do is you can take negative V, which I haven't told you what negatives are, but basically what a negative does is it just flips the direction that your vector is going. So V, negative V would just be the same V here, but going in the opposite direction. So let me try to replicate that here. So it's something like that. It's not the best drawing. Okay, something like that. It's not quite long enough, but we'll pretend. So this here is negative V. Remember, negative is just flipping the vector in the opposite direction. Okay, or rotating it 180. Maybe that's what someone meant earlier. We rotate the vector 180 degrees. That's another way to think about it, around this point here. So we like put our finger on that point and then just rotate the vector 180 degrees. And now how did this help? Well, if we then take this vector that we just created, oops, that's not the button I wanted to use. There we go. Okay, and we move this up here, like a head to tail thing. Okay, then we can see that the addition of U to negative V, if we add those two together, it's going from here to here. It's going in this direction. Okay, so that gives us, again, U minus V, right? Or U plus negative V, however you want to see it. Okay, so that there is our U plus negative V, which is the same as U minus V. Now, am I saying that this is how you should do the subtraction, is by flipping the V and then moving it over here? Not necessarily, but this, just doing that in your head without drawing the picture is going to tell you the direction you're going, right? So you see this is going from right to left. And so that's telling you, okay, I've drawn this diagonal. Which way does it go? Well, if I do negative V, it's going to be pointing this way. So the sum is going to be going right to left. So right to left. That's kind of what I do. I connect the tips of the vectors, and I say, okay, which way does it need to go? I kind of have this memorized, but sometimes I need to remind myself, and I do this kind of, I draw this picture in my head, and kind of say, okay, if I flip that and I move it over here, it's going to move from right to left, and so it kind of tells me right to left. Although if the vectors are sideways, maybe you're looking at up to down or down to up. So same idea. Does that help clarify some of that? Why, like, when we're gonna, which way the vector is going to be pointing? Again, there's always the memorization route. I'm not a huge fan of memorization, but if that works for you, it's a good starting point. Okay. Okay. So now the other operation we can do with vectors is what we call scalar multiplication. Okay. So we have scalar multiplication. Now, a scalar is a fancy word for basically just a number, a real number. Okay. So And the way we talk about real numbers, I should say scalars, is basically we can multiply. We can't necessarily multiply two vectors together, though we are going to learn tomorrow. We are going to learn a sort of multiplication for vectors, but we can multiply a vector by a real number, okay? So the way we do that is, and I'm going to introduce some notation. So lambda here is going to be a placeholder for real number. So if I had lambda times the vector ABC. So first of all, lambda is just some real number. So it's a real number, and this symbol you're seeing here is the Greek letter lambda. Again, maybe if you've taken some physics class or even a different math class, you've seen this symbol before. Mathematicians love to bring out Greek letters whenever they can. So it's the Greek letter lambda. If you've never seen it before, you can Google this and you can look at it, how it looks when it's typeset fancily. Okay, but basically when we multiply by a scalar, in terms of the what's going on in the arithmetic and the algebra, in the notation, all we do is we can think of it almost like a distribution here. We're distributing this over here. Now, technically it's not distribution, because distribution is when you kind of distribute through a bunch of things being added together. This is distributing through coordinates, which is not the same thing. But you can think of it very similar. It should feel very similar to distribution. So you have lambda A, lambda B, lambda C. So you see I've already gotten lazy with my lambda. Over here is fancy and curly. Over here it's already just getting much simpler. It gets, as I start writing more quickly, it takes longer. Okay. Now what's the picture here? Well, let's start with a basic vector. So let's start with just, again, a vector like, something like, my vectors are always going in the same direction. So try to do something like that. So this here, if this is our V, I can basically what scalar multiplication allows us to do is it allows us to stretch and it allows us to shrink, but it also allows us to reflect, do this, like, for example, we've already seen an example of it with this like negative V thing. Okay, but let's start with just the stretching and squishing. Okay, so for example, I can give this vector here something like this vector here. Maybe can be a little hard. This might be a little hard to see. Let me make it a little thicker. So you have something like this, this vector here. Hopefully that's kind of legible. This here is 1/2 times V, or something, maybe it's not exactly 1/2, but if you imagine it's going exactly halfway up this vector, we've taken the vector and we've squished it, made it smaller by a factor of 1/2. Okay. Okay. On the other hand, we can stretch a vector. So if you imagine we go all the way up and then it pops up out of the other side, and we have something like this. So again, this is starting at the same base point and it's going all the way up. Okay. Actually, maybe I should draw it. No, I think this is so I'm going to draw it kind of. Okay, so something like this. Pretend this lines up with this. I'm just drawing it here so that you can see the whole vector. Pretend it kind of lines up with this vector. This is maybe like 2 times the vector V. Okay. So scalar multiplication is you just stretch or you squish the vector. And then there's also like negatives, right? So if I multiplied by -1, I would get something like something like this. So this is -1 times V. So -1 times V. Okay. Cool. Any questions? I think the best thing we can do is jump into some examples. So we can. So someone's asking, a couple of good questions. Cool. So why is it not considered distribution? So distribution, like the distributive property, right, that you learned about, way back when, was when you multiply something by a bunch of numbers being added together. So a plus b plus c. Then if you multiply that by lambda, then you distribute the lambda and you get lambda a plus lambda b plus lambda c. Technically, we're not adding any numbers together. These are coordinates, right? These are the coordinates of a vector. And so you're not really distributing, but it feels exactly like distribution. So if you were to call this distribution, at some point someone might like correct you and be like, technically it's not distribution, but also it very much feels like distribution. So I think it's kind of fair to call it that. But, okay, so if two vectors are in different size, when we do addition, will it result in undefined? Yeah, so if by different size you mean like the coordinates, so you can only add together, you can do 3D plus 3D or 2D plus 2D, or eventually we're going to get to like 4D and higher dimensions. The dimensions have to be the same. So the dimensions have to be the same. So maybe I'll write that over here. So dimensions, their dimension has to match. Okay. Someone else is asking, can we scale by 0? Yeah. So what do we get when we scale by 0? Yeah. So if you do 0 times a, b, c, no matter what a, b, and c are, you're always going to get 0, 0, 0. And in terms of the picture, that's just a dot, right? So if you just this dot here alone, that's confusing because the dot's the same color. But yeah, just the dot is the 0 vector. Okay. Cool. Other questions? These are good questions. Okay, cool. Yeah, so I'm going to do some more examples. Don't think that we've just like, I'm just going to breeze past this and expect this to be enough for you to understand. Like, we're going to get to some examples. These are long lectures. We go until 9:20. So I do want to take a little break sometime in the middle. So hopefully we can, just take some time, look away from your screen. Don't, we stare enough at screens right now. So maybe we can just take like a 5-minute break. Okay. I did want to go back and reiterate something that I've remembered I remembered that I forgot. So just some notational stuff that you may have learned before, but I want to reiterate a little bit here because I think that's relevant here. So maybe in calculus, you learned this symbol here, this R with like an extra line over here, right? This is a symbol. What does a symbol represent? Anyone remember? Remember what this symbol, this fancy looking R. Yeah, so it's real. So it has to do with the real numbers. So this is the set of real numbers. Now, geometrically, what that means is like the number line. Right? So when we start talking about higher dimensional space, we're talking about ordered pairs of real numbers, ordered triples of real numbers. Later on, we'll get to even higher dimensional stuff. And so we want some notation that's going to encapsulate that too. And so this 2-dimensional space we call R with a power of 2. Okay, so R, you could say R squared. I think more commonly we would say something like R2. That's usually how they pronounce it. So R2 is how you would pronounce this. And just like that, similarly over here, you'd say R3. Okay. You can, if you say R squared or R cubed, I don't think you'll get funny looks or anything, but usually it's R2 or R3. That's usually how we say it. Okay. That's just another notational thing. It comes up a bit in the textbook. It usually is, all it's doing is setting up the context for the problem. So for example, if they'll say something like, let V be a vector in R2. And all that means is it's a 2-dimensional vector. Let U be a vector in R3. That's just saying it's a 3-dimensional vector. Okay, just some notational stuff because I did forget to mention that earlier. Okay, cool. So let's get back to what we were talking about, adding, subtracting, and scalar multiplication of vectors. Okay, so let's see some examples here. So here we have some concrete examples where we have actual numbers to deal with. So for example, this first example, we have the vector 1, 2, 3, and we're adding the vector 4, 5, 6. Okay, so we have 1, 2, 3, and 4, 5, 6, and we're adding them together. Well, remember, we just put these, I'm literally picturing in my head taking these three numbers and these three numbers, and I'm putting them on top of each other, and I'm adding every number that lands on top of another number. So this 4 would land on top of this 1. I add those together, and I get 5. Add the 2 and the 5, and I get 7. Add this 3 and this 6, and I get 9. So 5, 7, 9. All I'm doing is adding the 4 plus 1, 2 plus 5, 3 plus 6. Okay, that's how I get these numbers. Okay. Now over here, the second problem, just a basic scalar multiplication. 1/2 times all of this. 1/2 times 8 is 4. 1/2 times 4 is 2. 1/2 times 16 is 8. Okay, so all I did is, again, I'm going to use the word, even though that's technically incorrect. I'm basically distributing this 1/2 across these three numbers. Okay, and I end up with I just cut every number in half. If there's a 2 here, I double all of the numbers. If there's a third here, I divide them all by 3. Okay, so far so good, right? These are like the easy problems, right? And if it's like the very basic understanding. Okay, so this one we've upgraded a little bit. This one there's going to be a couple of steps, right? Because now we have some sort of order of operations. So we're going to do the stuff inside the parentheses first. So we get 2 times, and now we're just going to subtract these 2 vectors. And again, with subtraction, that works just like addition, where I subtract coordinate wise. So I do this coordinate minus this coordinate. So that gives me -1, 0, and -1. Right? So I did 1 minus 2, that gives me -1. 1 minus 1, that gives me 0. 0 minus 1, that gives me this -1. Okay. Now I can go ahead and multiply by this scalar, and that gives me -2, and then 2 times 0 is still 0, and then -2. So I multiplied 2 by all of these, and I get -2, 0, -2. And that there is our final answer. Okay. Okay. Any questions on those? These are sort of like the basic versions of sort of questions we can get here. Any questions on that? Nothing. I don't think anything too wild came out of these examples, right? This is pretty straightforward. I just wanted you to see even these most basic examples. Okay. Now I do want to do one that's a little trickier. Basically, we can, once we have all of this, we can kind of upgrade this type of problem to like these fill in the blank problems. Just like, when we were first learning how to add and subtract and multiply, right? Though I think that was stretched out over a longer period of times because I think just developmentally that's what it took, right? So you were learning how to add and subtract, and then eventually someone said like, okay, what if I don't, instead of giving you 2 numbers and asking you to add them together, what if I told you 3 plus this number equals 7? What does that number have to be, right? That's like the next level of understanding, right? So that's kind of what we're doing here. We're upgrading things. Now, in this case, we're upgrading them in 2 different ways. First of all, we're leaving these blanks, these constants, A, B, and that's supposed to be C, but it still works with just another B, right? A, B, and AB are just constants. They're just these placeholders, and they just don't mean anything. They can't be simplified at all. Okay, they can't necessarily be there's nothing to plug in for those. They're just there. Okay, so that's one of the things. You've hopefully gotten kind of comfortable with that, taking calculus and pre-calculus classes. We'd like to do that every once in a while. Just throw in these kind of these unknowns, these constants that just kind of hang out there, and it can't really be simplified in any way. Okay, but the other thing, our goal is to fill in these blanks here, these 3 blanks. Okay, our goal is to fill in these 3 blanks. Now, there's a couple of ways to go about this. You can kind of do a sort of guess and check sort of situation. You kind of figure out, okay, what needs to go in here in order for me to, when I cut it in half and then I subtract that from 27, I get this here. Okay, what needs to go there? Okay, and I can kind of reverse engineer that and figure it out. Or I can do this and figure out the same thing here. You can do it coordinate wise, so you can basically set this up as 3 different equations with 3 different unknowns in each, and just solve those. Or what I'm going to do is I'm going to kind of manipulate this whole thing as one big equation. So what I'm going to do first is I'm going to subtract this this vector here, this minus 27, 8, negative 7. I'm going to subtract this vector from both sides, just like if we were solving a regular old equation, right? Again, we're solving for these blanks here. So over here, they cancel. And on the left-hand side, I'm subtracting vectors. So I just do 2a plus 27 3b minus 8, negative 5b plus 7. Okay, all I did is I subtracted these 2 vectors. Okay, that's what I get here. And then on the right-hand side, I end up with just this negative 1/2, and then the 3 blanks I'm looking for. Okay. 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 And now I need to cancel out this negative 1/2. So, sorry, someone's coming with the question. Is it plus 27? Yeah, this here is plus 27. Yeah. Okay. And now to cancel out with this negative 1/2, I multiply by negative 2, right? Because negative 2 times negative 1/2 is just a 1. So now it just becomes multiplied by 1. So multiply everything by negative 2. So I multiply all of this, so times negative 2 times negative 2. So over here, they cancel. And on this side, I get basically just multiply everything by negative 2. So that's negative 4a minus 54. I see. That's why everyone's getting confused, because I made a mistake. So this is a positive 27. This 27 should also be positive, and this should hence be negative. There. I'll use a different color to highlight the correction. Yeah, good catch. This should be a minus 27 because it's I just goofed and added an extra negative sign there. Cool. So then this should be plus here. Okay. Multiplying again by negative 2, negative 6b plus 16, and then 10b minus 14. And now we've solved for these blanks. So I think on the online homework, you have actual blanks that you it's a computer, so you click and you fill in the blanks, and so you can kind of do this. That's kind of how you can go about filling in these, filling in each of these blanks. I will warn that sometimes the blanks are not all on the same vector. So you're gonna have like 2 blanks here and then 1 blank over here, in which case it's probably best to just set up an equation for each variable. So let me show you what I mean by that. Oops. Oh, come on. There. So like an alternative way to do this setup. Is you could just set up basically each coordinate on its own. So you have this, this, and this. So you have 2a is equal to 27 minus 1/2 times this first blank. And then you have the same thing for the second coordinate. 3b is equal to 8 minus 1/2 times the second blank. And I am going to scroll here just a little bit so you can see. We have negative 5b is equal to -7 minus 1/2 times this question mark here. Okay. And so this can kind of help you fill in some of these blanks, especially if the blanks are not all on the same vector. Okay. So for example, I think there's a homework problem where you have this one is blank, this one is blank, this one is given, and then over here there's a blank in the middle. Okay. So that that's something like that. If something like that were to come up, that's when you'd definitely want to break up this sort of setup here. Okay. Any questions on these this example here? Okay, cool. Cool. So give you a second to catch up on the writing. So these are the sorts of basic problems that we'll be dealing with. So if I looked over the online homework to make sure I'm not missing any major curveballs, I'm going to get to a few more stuff today, and then also we'll finish up this. We might not get through the whole section today. We're going to probably finish up the section properly like tomorrow, and we'll have be completed through it by tomorrow, the end of lecture tomorrow, or by halfway through the lecture tomorrow. And then we'll start another section tomorrow as well. A couple of the next thing I kind of want to discuss is actually kind of going back. So a few slides ago, I talked about the notation of vectors and how I like to use the angled brackets, and the book likes to use parentheses, even though I like to use parentheses for points and angle brackets for vectors. Okay, and the book just uses parentheses for everything instead of and they don't distinguish as much between points and vectors. So it's kind of what I want to talk about. So here, what we see is a point, the point 3, 2, right, which is in the coordinate plane, and it's 3 to the right and 2 up, right? As we can see that here. Then we have this vector, which is 3, 2. And the reason you know it's 3, 2 is not because necessarily that lives in coordinates, but because you kind of break it down into these two. If you break it down into these two parts, there's a vector of length 3 in this direction and a vector of length 2 in this direction, right? And so because of that, you can kind of say, okay, this is here is our vector 3, 2, and I'm distinguishing between them there. So this is kind of, in my head, this is why these two objects should be different. If you like to think in terms of like physics or something like that, in my head, a point is like a particle that exists in space, and a vector is like some kind of either a force vector or a velocity vector acting on that particle in space. That's how I like to distinguish between points and vectors. But like the textbook and the online homework and other situations don't always distinguish between a point and a vector, because they're very similar in a lot of ways, and sometimes it helps to just kind of think, well, you can think of this point as a vector back and forth. Definitely on the algebra side of things, that makes sense, right? Both of these are just a pair of ordered or an ordered pair of numbers. I just put different symbols around them, right? So anything I can do with a vector, I can do with a point. Anything I can do with a point, I can do with a vector in terms of the algebra. But the geometry is a little different. Like how does this vector give me this point and vice versa? Well, if you were to put coordinates on this, right? Oops, give me 1 second. If we were to put coordinates on this, oops. Then you can see that if I just go to the point here at the tip, this point here is 3, 2. So that point there is the points 3, 2. So basically vectors, if you base them at the origin, if you put their base at the origin, then they always point to a certain point in space. And that point is just exactly the same as the vector. And similarly, from a point, you can just cook up the vector by just starting at the origin and pointing to that point. Okay, so this is kind of how you can kind of think of points and vectors as the same, as like interchangeably. Technically, vectors, are slightly different, but you can say Again, I'd like to also sometimes like to think of vectors as like instructions. It's telling you start here, go here, start here, go here. That's what vectors are doing, which makes sense. That's how you add vectors, by putting them heads and tails. Start here, go here, then start here and go here, and then that adds together to just cutting across the diagonal. A couple of good questions are coming in. So someone's saying, is a point just a zero vector? So this is kind of the confusing part. If you should think of vectors as being based at the origin. So then a point in space is the vector going from the origin to that point. Okay. So you can think of points. So yeah, you can think of points and vectors as the same thing, kind of. I'll put that in quotes. Basically, because, algebraically, this makes a lot of sense because they're both just pairs of numbers. And in the textbook, it's like the exact same notation, a point and a vector and a vector and a point. Same notation, right? But what I'm trying to illustrate with my picture here is basically you can think of a vector as starting at the origin and pointing at a certain point in space. And so you can think of that vector as just the same as that point. So if you have a point in space, you can just think of it as the vector that points to that point. Points to that point. Okay. Someone have a question on that part of it? This is kind of a little abstract here, so it's kind of hard to wrap your head around. Now, for the rest of the quarter, you just want to think, okay, a vector is a point and the point is a vector. That's totally fine. I like to distinguish them a little bit because of the physical nature of it. So someone else is asking, is it true that vectors are speed and direction? So vectors are a little more just abstract than that. So you can apply them to different things. What you're describing is thinking of velocity in physics as a vector. And that's the speed is the magnitude of the vector, and the direction is, of course, the direction of the vector. And so that gives you, as a vector as a whole, that's velocity. Velocity is basically speed with direction. Okay. Questions on that? Yeah, so you can think of every point as just the vector that points to it. Okay. So a point is just the vector that points to it. Right. So if you want to get to a certain point, just tell me the vector that gets me there from the origin. But in terms of the numbers, it's going to be exactly the same, as we can see here. Right. The vector 3, 2 is the vector that gets me from the origin to the point 3, 2. Okay. Cool. So this is a little abstract, but yeah, just know that in terms of the coordinates and stuff, just like basically what this is saying is angle brackets parentheses doesn't really matter ultimately. The distinction is much more conceptual than anything else. Okay. I think when it comes to actually time to do problems, it usually doesn't hurt too much to just point and vector, same thing. Okay, cool. So now I want to highlight some what's called the standard basis vectors. Okay. Okay, so we have these three vectors here, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, if you were doing in 2 dimensions, it would just be 1, 0, and 0, 1, right? But these have special names. We call these I, J, and K. I've also seen these with slightly different notation. I've also seen them with instead of just the letters I, J, K, it's I, but the dot is a little caret. And the same thing, J with the dot is a caret. And then K, there's no dot, but we just add the caret there. I think the textbook just likes to use the letters, but boldface. Since I can't use boldface, I'll probably use, or when I'm writing, I can't use boldface. I'll probably use these symbols here. Okay. So bold if typed. Okay. Now, what's so special about these? Well, if we were to draw these in space, what would they look like? Well, I'm gonna use colors here. Basically, what these look like is they basically represent the three axes. So you have X, so this is your I, and then you have Y, which is represented by J, and K, which is representing Z. So this is your K. Okay. And so these three vectors kind of, the fact that, we call them a basis, all that means is that basically these are the three most basic vectors you can get in three-dimensional space. If it was in 2 dimensions, you just have I and J, and you just have 2 basic vectors, okay? And what it means to be a basis is basically that we can write any vector like this, any X, Y, Z, you can write it as X times I, Y times J, and Z times K. So now remember, so the confusing thing here is I, J, K are vectors, X, Y, Z are numbers or scalars, right? So what we're doing here is this is scalar multiplication, and then that gives you these 3 vectors, and you add them together, and it gives you this. So to make that more clear, you have X times 1, 0, 0, plus Y times 0, 1, 0, plus Z times 0, 0, 1. So this is kind of an intermediate step. If I was going to plug this in, I would put it in like as between equal signs between these two sides of the equation. This is kind of explaining why these two things are equal, right? So this is just, right, based on my definitions up here, that's exactly what these 3 vectors are. Now, if I do the scalar multiplication, I get X 0, 0 plus y, 0, Y 0 plus 0, 0, Z, right? The zeros kind of get rid of all of the scalar. Like if there's a 0 in a certain coordinate, it doesn't care about the scalar, okay? And so you can just, then when I add those together, the zeros, again, you get X in the first coordinate because there's nothing in these 2 first coordinates, Y in the second coordinate, and Z in the third coordinate. So you can just simplify and get this, okay? So this, this is kind of conceptually where we're at. You can kind of just accept that this is just another notation. You can kind of just, if it helps to like clarify things, you can just take this as, this is just another notation for vectors. You can write a vector. So maybe I'll do this. Come on. I'll do this as a little example. I'll try to leave some space here so you can still see and jot things down. But as a little example here, if I have the vector -1, 2, -8, I can write this as -I plus 2j minus 8k. So this is another notation for vectors that comes up sometimes, which is basing it, you can think of it as IJK notation. More properly, it would be writing your vector in terms of the standard basis. Okay, that's how you say it. Like if you were trying to impress your math professor, you'd say this is the vectors in terms of the standard basis, but you can also just think this is IJK notation. Okay. And this kind of slide here is just representing why we're allowed to, why we can use this other notation and what this notation actually means. Okay. Will it always be in that order? So that's one of the nice things is now this is actual addition. So technically you can write, it would be kind of silly. People would look at you funny, but it's totally legal, is to write something like this. Like this is totally allowed. It just looks funny and people would be like, why are you doing that? It's confusing, but it's technically allowed. What does it mean by basis in terms of standard basis? This is what it means. It means that you can write any vector in terms of these three vectors. Okay, so any 3D vector is in terms of these three vectors, which can't be said. Like if I just chose three vectors at random, that might not be the case. Might not be able to do this. I might not be able to break down the vectors, any vector in terms of those three vectors. Okay, so that's what basis means. It means they're kind of the basic building blocks for three-dimensional space, which I think this picture kind of encapsulates that, right? Like this gives you, these three vectors give you all the information you need to tell you that you're in three-dimensional space, right? Like you couldn't do this in two-dimensional space, right? You couldn't have three vectors like this in two-dimensional space. And in four-dimensional space, it wouldn't be enough. You'd need another vector. Okay. Cool. Any other questions?